Okay, let's do one more example of calculating Galois groups. Now, okay, so let Q be p to the power of n, p a prime number, and let's try to find let us study Galois group of FQ. So remember what this notation now means. This is a field with Q elements. Okay, so in what we're going to do, it doesn't matter which field with Q elements you actually take. This is some fields with Q elements. The Galois group of FQ over FP. Now any field with Q elements, well, its prime field is just FP, so you may as well just think that FP is contained in FQ. We're trying to calculate this Galois. Now, okay, so what is FQ? So FQ is a splitting field, of a x to the power of Q minus x over Fp. Okay, this polynomial here, this polynomial doesn't have any repeated roots, so it has no repeated roots. Well, one way to see that would be, one way to argue that would be that, well, it's got Q, every element of FQ is a root of it, so it's got, well, Q distinct roots, so it doesn't have any repeated roots. Or you could look at the derivative if you like. Doesn't have any repeated roots, so that means that any separable, so implies that any separable, implies that any reducible factor of it doesn't have any repeated roots, so any reducible factor of it is separable. So by the result that we saw earlier, so the Galois group of FQ over FP, well, how many elements does it have? The number of elements of it will then be equal to the degree of the extension FQ over Fp. Well, this degree, so Q being p to the power of n, this degree is equal to n. So the Galois group of FQ over Fp has n elements. Okay. Do we know one element there? Well, of course, identity is there. Do we know one non-trivial element there in that Galois group? Exactly, the Frobenius. Right? So the Frobenius, going from FQ to FQ, sending any alpha to the power of p. So because FQ has characteristics, let me just remind you of the argument. FQ having characteristic p would imply that this is actually a ring homomorphism. Now FQ is a field, so it's going to be injective. Now it's an injective homomorphism from FQ to itself. Because FQ has finally many elements, any injective map from FQ to FQ is also surjective. So this is going to be an isomorphism of FQ, and well, any ring map from FQ to FQ is going to fix FP, right? Because it has to send 1 to 1, and then it would have to fix every element of FP. So this is in, so consider this. This is in, well, it's an automorphism of FQ and fixes FP, so it's an element of the Galois group of FQ over FP. Now, well, I mean, so okay, so to fix FP, you could argue that it's a ring homomorphism, so it sends 1 to 1, so it would have to send actually act trivially on the prime field, or alternatively, if you wish, just refer to Fermat's little theorem for any element of Fp. well, any alpha in Fp, alpha to the power of p is just alpha itself. But anyway, so Frobenius is an element of this Galois, raising things to the power of p. Okay, let's consider the subgroup generated by Frobenius. So we're now going to compose the Frobenius with itself. So let's see. So let's think about the subgroup generated by Frobenius in the Galois group. Okay, so we're going to compose Frobenius with itself. Now, if I look at Frobenius, if I compose it with itself 8 times, so if I compose it with itself twice, I'm going to write Frobenius 2. By that I mean compose Frobenius with itself twice. Let me make sure that you have the camera. So again, this notation means FR over FR. Okay. Now, if I look at Frobenius squared applied to alpha, okay, so now that's Frobenius applied to Frobenius at alpha. Okay, so that's now, this is alpha to the power of p, and then further to the power of p. This is alpha to the power of p to the power of p. It's alpha to the power of p squared. Similarly, if you look at a Frobenius to the power of a of alpha, a being an integer, this is just going to be, a being positive integer, this is just going to be alpha to the power of p to the power of a. This is for every a greater than or equal to 1. Okay. So these are powers of the Frobenius, right? Compositions of Frobenius with itself. Now, okay, our group, this Galois group is a finite group, right? This is a finite group, order n, q being p to the power of n. This will have order. Now, any element of a finite group has finite order. So let's think about the order of Frobenius. It's a finite, it's a number. Frobenius has finite order, and that order will divide n. Let's see what that order actually is. Okay, so to calculate that order, we need to find the smallest a such that Frobenius to the power of a is identity. So what is the order of Frobenius in the Galois group?